What I want to do is take you down memory lane with respect to uh, electron emission. So coming here, do you recall in general chemistry that on the y-axis we have energy, and we could have an electron in a low energy state, and then we could have a higher energy state. And that little arrow there is representing a electron. To remember that if I take a photon of light and I shine it on this atom, what we can do is promote this electron to a higher energy state. So let's promote it. Okay, now it's in a higher energy state. Now, electrons, atoms, life, we don't like to be in a higher energy state. So eventually that's going to relax back down to the lower energy state. And when that electron relaxes back down, it emits a photon of light. All right? So if we come back here to the slide here, what's happening here is that nuclei will not be able to absorb a photon of light from the radio frequency shown here. So what if we say, hey, now let's look at it like this. Let's take an electron, a nucleus, and place it, and that nucleus is in a low energy state. We cannot, let's zap it this way here. We cannot take a radio frequency photon, shine it onto the molecule, and promote it to the higher energy state. It does not work. And the reason why it doesn't work comes down to this concept of spin states. A nucleus, okay, has nuclear spin. So what we have here is if we draw a proton, let's draw a proton here, just a little. So what I'm drawing is a circle trying to represent a proton. Okay? Now that proton we know is positively charged. So it's a charged particle. And that charged particle is spinning. It's spinning fast, okay? So the nucleus itself has a spin state. And when you take a object or particle that's charged and it spins really, really fast, what happens is it generates a magnetic field. And that magnetic field looks like this. Okay? Try and draw these arrows here. And it creates this magnetic field. Okay? And so this magnetic field, kind of analogous, looks like a bar magnet. And when we have a bar magnet, we know we have a north pole and a south pole. So when we're looking at the nuclei of atoms, we kind of think of them as a bar magnet, and they have a north and south pole. And when the nuclei is oriented in this direction, right here, pointing up, we call that a alpha state. And we assign a spin number to that state as a positive 1/2. In contrast, you can have a other state. let's give ourselves some more room here, where it's the opposite. All right, let's draw ourselves some better arrows there. And that is called the beta state. And that has a spin value, a nuclear spin of negative 1/2. So what we have now is two states, the alpha state and the beta state. And the alpha state and beta state are at the same energy level when there's no magnetic field. Absolutely the same energy. But the moment you place those nuclei in a magnetic field, right, they align in two energy states. So what I'm going to now do is I'm going to then represent something called B or beta, beta EXT. For the beta represents a magnetic field, and that right there means external. So what we have is an external magnetic field generated from the magnet on the NMR instrument, and then our nuclei has an internal magnetic field generated from the proton itself. So when you take your atoms or your nuclei and place them into a magnetic field, so this, we're going to represent a nuclei here with this blue arrow. We can now zap it with radio frequencies, and now because it is in a magnetic field, we can now promote it to the higher energy state, represented like that. So this right here would be the beta state, and that is the alpha state. We could also represent negative 1/2, positive 1/2. Now when that nuclei is in the beta state, that's a higher energy state. And then that can relax back down, into the alpha state. And when it relaxes back down, what happens? We emit radio frequencies. And then the detector will detect that emission, and that will help us understand the structure of the molecule. So, in summary of that little mini lesson there, atomic nuclei cannot go into a higher energy state unless it is in an external magnetic field. And that little bullet point right there just talked about exactly what I've already talked about, that the alpha spin state corresponds to the plus 1/2, and the negative 1/2 corresponds to the beta state. That's all just a rehash of what I've just talked about. Now this slide right here is rehashing everything again, but it's really, really important to understand this concept that when nuclei are not in an external magnetic field, the energies of the two states, the alpha state and the beta state, are exactly the same. But, so that's what this is representing right here. Okay? These nuclei, so each one of these arrows represents nuclei. And you can see the blue ones are in the alpha state, and then the red ones are in the beta state. But the energy of those two are represented with this line right here. And they are the same energy. And you can also see that the orientation of these nuclei are all random, just random all over the place, right? But the moment that you place these nuclei in an external magnetic field represented by this green arrow, what happens? The randomness goes away. They align. The alpha state, you can see here, aligns with the direction of the external magnetic field. Whereas in the beta state, it is opposing the magnetic field. Now, the way I remember the energy states is I kind of look at it like a river. So the external magnetic field is the river. And so a lower energy state would be swimming with the current. As you can see, the blue arrows are in the same directionality, so it's flowing with the current. But the red proton or red nuclei are trying to swim upriver. And from personal experience, you can relate that that's a whole lot more work swimming up a river than swimming down the river. Okay. And so what happens here is we have two energy states, the alpha state and the beta state. And we have the energy difference between those two states. So that's what the delta E spin it talks about or is representing, the energy difference between those two spin states. Now, this energy gap right here between the two spin states is proportional to the external magnetic field. That's very, very important. So let's go here and draw a little diagram right here, okay, to show you what I mean by that. So when we go and purchase an NMR instrument, okay, now these instruments are very, very expensive. We can buy an instrument that, let's say, is 300 megahertz. Now, this term right there, 300 megahertz, is just telling us the strength of the magnet. So you could purchase a 500 megahertz instrument and even an 800 megahertz instrument. And that's just measuring how strong the magnet is. So what happens is the change of the energy states is going to be larger with the stronger magnet. So remember, we have the same energy state for the alpha and the beta. When we place it into an external magnetic field, what happens? It splits. All right. So we have an alpha state and a beta state. And that distance right there is the change in energy of the spin. But if you use a stronger magnet, let's say the 500, here's our alpha, there's our beta, what happens? That gap right there gets larger. And then you can see if we get to the 800, then it's going to be even bigger, right? So that's the concept here. So that change in energy is going to be different depending on the strength of the magnet. And so what we have here is a relationship. And that relationship is that the change in energy of the spin is going to be proportional to the external magnetic field. Now, what is that word? Spin. Like, why do we call it the change of energy of the spin? Well, the reason why we call it that is because when you have your nuclei in an external magnetic field, what happens is that you are going to zap your sample with the radio frequencies, and when the nuclei absorbs that photon of light from the radio frequency spectrum, what happens is it gets promoted to the higher energy state in the beta state. And you can see that it goes and the arrow flips. And so what's happening is we go from an alpha state to a beta state, and we call that a spin flip. Now that makes sense, right? A spin flip, because that is the plus 1/2 spin state. And then when it gets absorbs a photon of light and gets promoted, what happens to its spin state? It gets flipped to the negative 1/2. And then when that excited nuclei relaxes back down, it's going to emit a photon of light in the radio frequency range, which then the computer and the detector will detect that. So that right there, the spin flip, is just another name for resonance. So when we go back and look at what does NMR stand for, it stands for nuclear magnetic resonance. So that process of spin flipping right here, when we spin flip a nucleus, what's happening? It is resonated. And resonance simply means that the nuclei right there is absorbing a photon of light. Okay. Let's see here. All right. Now, when the beta state returns to the alpha state, it's the radio frequency photons that are emitted, and our detector is going to get that, and that's going to help us determine the structure of our molecules. Okay. Now, what helps us understand the structure of molecules is not all nuclei are going to absorb the same frequency. Every nuclei in the molecule is going to absorb at different frequencies. And based off of those different frequencies at which they absorb is information that the chemists and the physicists use to help us determine the structure. It's really, really cool. We're going to learn a whole lot more about that in subsequent videos. That's going to make a whole lot more sense later. Okay. But another interesting thing that you need to be aware of is that not all nuclei are created the same. Not all nuclei are NMR active. And what I mean by NMR active is if you place a molecule into the NMR instrument and click go, it may not work unless you select the right nuclei. And in the most common NMR that we use is called a proton NMR. And that's what this right here is showing us here. H standing for the hydrogen atom, which is another way of saying proton. So hydrogen atoms are protons. So we call it proton NMR. Okay? And one critical thing in determining which nuclei can be used in an NMR experiment has to do with this number right here. How many protons it has. And the number of protons has to be odd. So proton NMR has an odd number of protons, so it can be used in NMR. Another very common nuclei that we look at in an NMR instrument is carbon-13. Those are two very common nuclei that organic chemists look at in an NMR experiment. Another one that is gaining momentum in the field is fluorine NMR. But not all atoms or not all nuclei are NMR active. That's really, really important to understand. So in the next video, we will now delve into understanding that not all nuclei are created equal. Hence, they're not all going to absorb the same frequency when they are inside the NMR instrument. So that's what we'll talk about in the next video.